Okay, we're going to go ahead and get started with section 9.4. I'm probably going to go 2 pages at a time and then stop the video and start posting. Okay, so this section is called Radius of Convergence. In this section, we will develop a strategy for finding the interval of convergence for an arbitrary power series and backing it up with some proof. To begin, we have power series in this form where there's some constant times x minus a to the n. If we substitute an a in for x, this is going to go to 0. And we say that that converges, assuring us that there is at least one real number that exists where the series converges to a value. Some power series converge for all real numbers, like what we saw with the Maclaurin series for sine, cosine, and e to the x. If you recall, when we opened up the interval of convergence and we kept adding terms to our polynomial, the function and the power series, or the series, they would lie on top of one another. And then finally, we learned from dealing with base and our variations from base that we might have something called an interval of convergence. In this chapter, we'll learn how to use a special test to help us generate intervals of convergence. So that leads us to Theorem 5, the convergence test for power series. So there are 3 possible scenarios for dealing with a power series in this form. The first case tells us in a mathy way that we can find an interval of convergence. We'll converge on the interval of convergence and diverge otherwise. We may learn that the series converges for every x value that exists. In that case, our radius of convergence, would be infinity. And finally, we may have a case like case 1, or the case above, where the interval of convergence only happens at one point when x equals a. So that would mean our radius of convergence is actually equal to 0. So again, r is the radius of convergence. We say that the set of all x for which the series converges is called the interval of convergence. First, we'll learn how to find the radius of convergence, and then later on in section 5, we'll learn how to determine what's happening at the endpoint. So let's just do a quick visual example. Let's say we figure out that the interval of convergence goes from -2 to 1. So I could plot this. Here's 0, and here's 1. Open circle at -2, open circle at 1, fill it in. That's our IOC. Now to find the radius of convergence, what we should do is, I know that if I measured this is 3 units long. So I go halfway. Halfway would be at minus 0.05. And I draw my radius from there to one of the endpoints. And then I measure. That is 1.5 units long. On the next page is something called the nth term test, and we say for a series to converge, the nth term must go to 0 as n approaches infinity. So in other words, as we start writing more and more terms, they're getting small and smaller, not contributing very much to the overall sum. If the partial sums are approaching a limit, then the partial sums must be getting close to one another, very close to 0. And that's what this is telling us. We say for a possibly convergent series, if I take the limit of our series and I take the difference of 2 of the partial sums way